If you ever want to use these WS2812 Neopixel LEDs with your PIC project but not sure how to do it, this is a video for you. They're actually pretty easy to drive once you understand the timing involved. I'm going to show you the C code that I use to do that and how easy it actually is. Nothing difficult about it, no complicated assembler or anything like that is needed, and we'll get right into that in a second. If you want to follow this demo at home, you'll need to solder together some WS2812 LEDs the way that I've done here, with a couple of wires and decoupling capacitors on the power supply, the 5V and ground, and then I linked in the data out from the one chip to the data in over the next, and so on until they're all connected together. I've used a PIC 16F1613 for this, a small PIC device. The only critical factor in choosing the PIC for this is it needs to run at 16 MHz internal clock speed. And that is so we can meet the timing requirement for the WS2812. And then I additionally have connections to the PIC 3 programmer on the breadboard there, and you can also see a button, and this is how I have it connected. Just the usual 5 connections to the PIC 3 programmer, and one output for the LED drive, and I'm powering it from a separate 5V power supply, as the PIC 3 probably can't provide enough power to drive the LEDs if they're all turned on at once. So let's look at the timing. Now this part of the data sheet in red here, boxed in red, is the key part which tells you about the 1 and 0 pulse timings. But what does that mean? Let's have a look. To send a 0, we send with a short pulse with a low following it, and the 0 value should be between 250 and 550 nanoseconds for the high period. Now to send a 1, we send a slightly longer pulse followed by a low period, and the 1 should be between 650 to 950 nanoseconds. Now both of these have a minimum low period, which is not too critical, which we'll easily meet in the software, so we don't really need to worry about it, but I'll put it on here anyway. For the 0 bit, 700 nanoseconds, and for the 1 bit it's 300 nanoseconds. So to send data, we just simply string these pulses together to make up the 8 bits that we actually want to send. So if we want to send starting with a 0, we send a short pulse, and then a 1, we follow it with a longer pulse, say another 1, another longer pulse, and then a 0, a shorter pulse, and we just keep going like that, stringing them together until we have our 8 bits for one LED like this. Each WS2812 of course has 3 LEDs inside of it, and each one has a value, an 8-bit value, 0 to 255, to indicate its brightness. And the way that you send that data is you send the first 8 bits that you send are the green, and then you send the second 8 bits straight away after that are the red, and then followed of course by the blue. So each LED that you have in your string has the 24 bits there for each 8-bit value, and then you just carry straight on after. If you've got more than one LED, you just go straight on to the next LED and you just keep going as many LEDs as you've got. So that is our LED 1, and then over there the next one as we start is LED 2, and you just keep going, just keep sending data until you've satisfied all the LEDs in your string, and then at the end of that string the data line has to go low for at least 50 microseconds, and then you start refreshing the LEDs again, beginning with LED 1, the whole new set of data going out. Okay, so let's get started with a new project using the MPLAB X IDE. Just OK that. We're going to select our device from here, baseline 1613. OK that. PIC kit 3, latest assembler or compiler that I have. Project name, let's call it WS2812 demo. Finish. So that's our project created. Now we use the configurator to set up the chip. It's by far the easiest way. I would always recommend using the configurator. Save the file. So important thing is that we use the internal oscillator, and we need to select 16 megahertz. And the reason we need to do that is so that we can get the right timing, fast enough timing, short enough pulses on the signal that's going to drive the WS2812. So the other thing we need to do on the pins, we need to select pin 7 is going to be our output pin. So we simply select that as an output, and pin 8 is going to be our input pin if we need that button. General purpose input. So we need to deselect analog. I don't know why it selects analog automatically there for the output. Doesn't make any sense. And for the input pin, we just want to select weak pull-up, so that we don't need to put a resistor on there for the switch to pull it up. When you do use weak pull-ups, there's an additional setting you have to change in here, which enables all of the weak pull-ups. If I can find it. This weak pull-up enable. We set that to enable. Have a look at our notifications here. It's always worth checking the notifications to see if there's anything that is a problem. There's nothing that's a problem here, except that we don't need low voltage programming, so we'll take that off. And all now looks good. And that's all we need to set up for this project. We don't need anything else. So if we generate the code now, it will generate our project code for us. Once that's finished, we can close that down. Let's write some software, some functions here to send a 1-bit and a 0-bit. So let's start with sending a 1-bit. This is going to be a long pulse. So let's start with that. Let's call it a 1 pulse. And what we need to do is set the output pin, which is the LAT-C 3 pin, and we need to set it to a 1, and then we need it to stay 1 for a period of time. So to do that, because this is the long pulse, remember, so we need to send 3 set to 1s for that pin. And now, of course, only the first one will really do anything, but the second 2 will take up time, and they actually take up less time than a knock. So it's better to do it like that rather than to use a knock, is what I found. And after that, we want to set it back to 0 again, because that's the end of the pulse. So that's all we need for our function, to set our port pin to a high for a certain period of time, and then back to a low again and that will send us a 1 pulse. So now what we want to do is a 0 pulse. So a 0 pulse is essentially the same. Set it to a 1, and then after a short period of time afterwards set it back to 0. So the 0 pulse, we want it to be high just for the shortest possible time, so we just have the one line of the one set, effectively set bit to 1, and then immediately followed by a clear bit to 0, and that will generate our 1 and 0 pulses. Okay, so let's put these into our main loop, program the chip, and see what timing these give us. So let's copy that down into our main loop here. I've already copied in the 0 pulse, so the I should have put in the that's a 1. Let's just change that. We have a 1 pulse in there, and let's actually copy that again and do 2 of each in our loop here, and then I'm going to follow that with a delay, just a small delay, so that we can see the actual spacing between them. Okay, so let's program our chip, and we should see our pulses, and we can look at those on the scope that we have here, the picoscope. So we wait for that to program, and then we should see some pulses pop up on here. And there we go. We'll let it settle. Yeah, there are our pulses. So we can have a look at the timing on these. See what we have here. So here we have a 249 nanoseconds for that's the low pulse. 1.5 microseconds for the idle time in between the low part of the pulse, which is longer than the spec suggests, but it doesn't matter. This is our 1 pulse, which is 746 nanoseconds, which is within the spec, and then we just repeat it so that there's a low period following that, again about 1.5 microseconds, which is absolutely fine. Okay, so we're happy with that our pulses are giving us the right timing. It's going to make the LEDs work. And so what we want to do now, we can remove that. We want to create a function to output the entire byte, one entire byte, 8 bits to the LED. And I have actually already prepared one earlier, which I'm going to copy in to here. So this is the function which I've called WS send byte, and the byte we're going to send it is K, which we'll pass to this function when we call it. And so it's going to send the bytes, the bits rather. So it uses the 1 pulse here to send a 1 pulse and a 0 pulse here, depending on each bit in the K value. So the first one is going to look for the top bit in K being a match for that top bit in our mask here. So we're ANDing them together, a bitwise AND. So if the top bit of K is set and the top bit of this is set, which it is, then it will output a 1 pulse. If the top bit of K is not set, in other words it's a 0, it will output a 0 pulse. And then we do the same thing for each of the bits in K. So this one's going to look at the 6th bit, and then the 5th bit, and then 4th, 3rd, and so on, all the way down to the 1st bit. So all we need to do in our program, in our main loop, is we copy that, and we can now say output a byte. And what value should we output? Well, let's output 101010, binary, so let's do it 10101010. So that is just a value. Every other bit set. Let's program that and see what that does. So that's finished. So we look at the scope, and so that's what. Let's have a slow that time base down just a little bit, so we can now see that we have 1, 2, 3, 4, 5, 6, 7, 8. We have our 8 bits. We have a 10, 10, 10, 10. That's looking pretty good. But our LED, of course, does need 3. There are 3 LEDs in each device, so we actually need to send 3 of these. So we simply, for a moment, let's just copy that 3 times. So now it's going to be for the what is it, green, red, and blue LEDs. We're going to be more saying value there, so it's going to light up all of the LEDs, approximate white. So let's program that. So that's finished. Let's have a look what we get on the scope this time. Let's slow that down a little bit. So now we can see that we have certainly more. Well, if we counted them, I'm sure there'd be 24 bits there. And so let's see what that effect that has had on our LED. So yeah, that's lit up as expected. So now for a little bit of a neater code, what we want to do is put those 3 values or those 3 calls there into a function of their own, a function that will write the data to one entire LED, and we do that like this. So we've got our 3 send bytes here for green, red, and blue, and in the declaration here we just create a 8-bit value for red, green, and blue, which we pass to that. So now each time for each LED in our string, so we have 3 in our test here, so we could call this 3 times with an RGB value, and that would light up the LED with whatever color we want, and we could just do that for as many LEDs as we have in the string. So now let's do a demo of this using this, and we write to our 3 LEDs in the string that we have here, and we'll give them each a different color so that we can see the effect of that. So it's RGB, so let's make the first one red. So let's just make it not too bright, because these are actually pretty bright. So red, 64 red, 0 green, 0 blue, and let's do the next one. 0 red, 64 green, 0 blue, and the last one will be 0 red, 0 green, and 64 blue. So we should have each of the 3 LEDs lit up in that red, green, blue, so we should see them. Okay, let's program that and see what we get. Yeah, okay, looks like it's programmed them, red, green, and blue. So then if you want to get a little bit more adventurous, you could program something a little bit more dynamic like this, which is going to flash the LEDs, different colours. It's worth noting that the time it takes to transmit that data for the 3 LEDs is, in this case, about 216 microseconds. So it's not too long. So the other thing I need to mention before I finish is the effect of interrupts on this code. If you run it as I am in this demo, in the background main loop, of your program, any interrupts that occur that happen in the high period of any of these pulses will ruin the timing of the LED data, and it won't work. So you need to prevent that from happening. So you can either do that by disabling interrupts before you send this data and then re-enable after, or by putting the LED updating routine in an actual timer interrupt itself, in a high priority one, and then it won't be interrupted by anything else. Hope you've enjoyed this video, found it useful. If you have, please like and subscribe.